Good evening and welcome to the BS and Beer Show. BS stands for Building Science. Tonight, our topic is vapor management. And this year we're trying some new things. For one, the show will be 60 minutes long instead of 90 minutes. And we're trying to keep it more informal and focused on a topic. And we might not even have guests sometimes. Obviously tonight we do have a very special guest. Not only is she an expert in vapor management, she's an expert in Zoom apparently, and can troubleshoot and keep her cool in very stressful situations with hundreds of people watching. So I'm Mike Maines in Maine. I am drinking a homemade tropical rum drink. Or I already downed the first one. There may be another one on the way. Let's see, BS and Beer is an independent grassroots movement to share building science knowledge through local meetup groups and this our Zoom show. The brew crew and our guests volunteer our time each month to bring what we hope is a fun and informative discussion. We encourage you to start your own local group. For information on how to get started, visit thebsandbeershow.com or check out our December 2022 show on YouTube. And I would like to thank our media partners, Green Building Advisor and Fine Homebuilding Magazine. Just a few quick announcements. Find the chat box icon at the bottom of the screen, post questions and comments there. Please be sure to click all panelists and attendees, or everyone, depending on your computer. Otherwise, Zoom reverts to panelists only, which means only we can see your comments. Fine Homebuilding sends out Zoom reminders every month. If you want to receive those as well as other information on the shows, join our mailing list at thebsandbeershow.com. Our mailing list is separate from the Zoom end of things. Or to learn about the show, check out Kylie's monthly BS and Beer post on Green Building Advisor. Finally, the video recording of tonight's show will be available at Green Building Advisor, and all past shows can be found on YouTube and through a link at thebsandbeershow.com. Let's see. Maybe if we just go around the screen and the brew crew introduces themselves, and then we'll introduce Christine. So how about you, Travis? Lead us off.
Yeah, we'll do this like the Beastie Boys. We'll do a little pass the mic. So I'm Travis Brungart. Thank you, Mike. I have a Fields and Ivy in my hand. That's a local Lawrence brew. And of course, I'm thrilled to have all of you here, all 135 of you, as well as my good friends on the BS and Beer Show. I don't have anything else to tell you except that the Mid-Atlantic Building Science Symposium registration is open. You can hit up bsandbeerkc.org for that. And then I'll pass the mic to Emily.
All right. Hey, Emily Mottram, architect here in Maine. Most of you know who I am. Sadly, it is dry January, so it's water tonight. I thoroughly enjoyed my holiday season, so back to some water for January. I'm glad to see 135 people here. It's January, so it's a great time to cuddle up from your computer and talk a little building science. And hoping that Christine's going to talk a little bit about vapor and the difference between warm climates and cold climates. So kind of be exciting tonight. I'm going to pass it off to Ben.
All right, I'm pretending to be Travis tonight, according to Zoom. This evening, I'm drinking a Jefferson's Reserve single barrel old fashioned. My little piece of news I can add is you can join Travis and I at IBS in a couple of weeks in Las Vegas. Yeah. We're going to be running the Performance Building Zone for 3 days, 17 sessions, back to back, all 3 days. We're going to be joined by Joe Cook, Ben Morton, Jordan Smith, Tim Euler, Garrett Davis, Dave Cooper, Mark LaLiberte, Randy Williams, Enrico Bonalari. Who else? Ross Trethui, Joe Stebrick, Jordan Smith, Aaron Jones, and Glenn Mathewson. So we've packed a whole bunch of smart people into a very short period of time. So come hang out with us and come have a beer at the end of the day.
I'll drink to that.
That
is
is
exciting.
Quickly becoming the best part of IBS. Is absolutely is the high performance building zone that Ben did. I had a great time. Well done.
It was great having you. Yeah, thank you. It's exciting. So let's talk vapor.
Yeah, so just let me give Christine a quick introduction, and then she can fill in with some more info. As founder of Building Science Fight Club, Christine Williamson provides technical consulting services for architects, developers, and contractors. She assists with design development and reviewing details and specifications to improve durability, comfort, and energy efficiency. She also teaches architects in training, and other building industry professionals about building science and construction. Christine, I just realized, I think that might have been an older bio. Is that still accurate? And is there anything you want to add about all of your various pursuits?
I'm basically retiring. I have a newborn and I have no idea. I don't actually know what day of the week it is. Like legitimately, I have no idea. You told me to show up and I showed up. It's a miracle I'm here. No, I'm taking a little bit of a break, but yeah, that's all still just about right. I'll be back at work in the fall. Officially. I mean, it's amazing how much work not working is. Anyway, but I'll be back working in the fall at Virginia Tech, where I'll be a professor of architecture. So I'll be teaching this kind of stuff, building science and vapor control and all kinds of stuff like that to architects in training. I'm pretty excited about that, really, to be in a not in a construction program or an engineering program, but in an architecture school teaching actual I guess architects in training. That'll be really nice. I love that Virginia Tech is really making that kind of commitment to equip architects with a little bit more technical knowledge to better position them for practice. So anyway, so that's what I'll be doing. That's what I'll be doing soon. But right now I'm a mom and very much enjoying a Modelo.
Nice.
I was really, people asked me what I craved in pregnancy, and I craved fruit in early pregnancy, like citrus. I really wanted a lot of citrus. And then beer. I wanted beer all the time. I think it was allergy. I just really wanted beer.
I got to confess, Christine, I also craved beer during your pregnancy. So I think it's totally justified.
It's fine, fair enough. So should we talk about vapor?
Yeah. What is water vapor? Or when we say vapor, do we always mean water vapor, or are there other forms of vapor we're concerned about? Or,
Like the vapors if you get verklempt?
Yeah, the vapors.
Smelling salts, vapors.
or ammonia vapors, chlorine vapors. Like what's important? Why does it matter?
So I think actually we have that's a good place to start, because one of the big problems in our industry among professionals is that we're really kind of confused by like why it is we're even having the conversation about vapor. And so one of the things that I find, I teach a lot of architects in training. And one of the things that I noticed that really, I think, contributes to this problem, because this is confusing enough on its own, like just the physics is confusing, but we make it worse. And the way that we make it worse is we tell people, or architects will ask me all the time, especially students will ask me all the time, they'll say, where does the vapor barrier go? Is what they ask for. Where does the vapor barrier go? Where do I put the vapor barrier? Like, okay, well, we're starting this way down the line here. Like back up some. Does our assembly even need vapor control? Like, what are we actually trying to do? And I think that we sort of think in terms of products that we need to buy as opposed to things that we need to achieve. And as soon as we reset our minds a little bit to say, okay, what is it that we're actually trying to achieve here? The whole conversation gets a lot easier. The second problem with the conversation about vapor is that people know that it's hard, and so they stop thinking. They go into some sort of like intellectual survival mode, and they're like, just tell me where the vapor barrier goes and I'll just memorize it and that's it. Like, just tell me. Climate zone, whatever, this kind of building, I'll come up with a matrix and I'll memorize it and we'll call it a day. But they actually stop thinking. And I would say about 75% of the questions that I get about vapor is stuff that people know the answer to. I'm like, you're not thinking, like you stopped thinking. You already know, stuff. You just stopped thinking about what you know. Like they forgot how they build normal walls. standard walls. Anyway, so I think it's because we go into this sort of survival mode, that we forget what we already know about buildings. And where we should really start is this conversation should really be about durability. And we have zero interest in controlling for vapor apart from durability. Water vapor. We were talking about like chlorine or whatever.
That's life durability.
Yeah, or vaping, whatever. Yeah, when we're talking about water vapor, the entire discussion is about durability. It's not about comfort. It's not so, and that actually is sort of a little bit tough because other materials that we're talking about in building science and in design, like insulation, has a lot of functions. It's about energy efficiency, it's about comfort, it's about condensation control. Like insulation does a lot of different things. Even water control layer, it's standard in North America to make our water control layer also our air control layer. It's not always the case, but oftentimes that's the way we end up doing things. And so we have a lot of things that sort of double up when we're talking about in their function. When we're talking about vapor control, our only concern is durability. That's it. And I saw someone mentioned occupant health in the chat. It's sort of down the line. It's the occupant health component of vapor ends up being related to durability, right? So if we have a condensation problem that leads to mold or decay or whatever, that can cause structural problems and that can cause occupant health problems. But when we're talking about the enclosure itself, this vapor control issue is durability related. So all we want to do is protect the building materials themselves from damage. That's it. So, and I think it really like that, for me, that's sort of an aha when I was learning this, and I'm sort of still learning it, but that was a big aha moment is protect the materials themselves from damage. That's what we're doing. And that kind of should inform everything else down the line. It's not about maintaining a certain humidity inside. That's part of the mechanical system will control or may or may not do a good job of controlling what the relative humidity inside is. But our interest in enclosure design with vapor control layers, retarders, barriers, whatever is a question of durability. So I think that's the best way to start the conversation is understand what it is that we're trying to do here. You don't need a vapor barrier for the sake of having one. You need a wall that doesn't rot. That's what you need.
We run into issues too because people, there's so much confusion in language. Somebody at summer camp this year said that we have to practice precision of language. Just today, I had a conversation with a very intelligent architect who was practicing high performance building, and he was asking me what kind of vapor barrier I'm using on the outside of the building. And I'm like, I want to pull my hair out because I'm like that you of all people should know, but it's we lose the practice of making sure we're using the right words and the right terms. And it's difficult. And I understand that it takes time to learn it, but we all need to do a better job of trying to call things what they really are and understand things what they really are. So there isn't confusion.
And it's not just, it really does hold people back, like other people. Like you may know what you mean by air vapor barrier. Like you may know, like if you're talking to someone when they say air vapor barrier, what they're really talking about typically is neither air nor vapor. They're talking about the water control membrane. But like I know I've sort of translated that in my mind and I know what they mean. But when we're unclear with this terminology, it leads to the where do I put my vapor barrier type questions where I'm like, well, okay, like what are we trying to do? What's the wall? What's the context? What are we doing? But yeah, the precision in language is a really big issue. And I think that leads to actually something else helpful in thinking about vapor control. And that is that materials, this concept of permeability is very important when we're talking about vapor control. So all materials are either more or less permeable to the passage of water in the vapor form. So, and this typically jives with our intuition about these things, right? So we know that like glass, metal, rubber, stuff like that doesn't allow a whole lot of water through. If I put I can carry a goldfish in water in a plastic bag. Like, I mean, that's like, we're talking liquid water, not water vapor, but anyway, it tracks with your, if I put a wet towel in a plastic bag and tie it up and leave it at the bottom of my my gym bag or something for a week, it'll still be wet at the end of the week. We haven't had a lot of, anyway, so we have a good intuition, fortunately, about many of our building materials. But if I had a wet towel in a canvas bag and left it for a week, it would be significantly drier, because we have drying through, say, canvas or a fabric bag or something like that, and not in a plastic bag or a Ziploc bag or something like that. But anyway, the point though is that permeance is a characteristic of all materials that we build with, in the same way that mass is a characteristic, or color, or density. Like, so we ought to be thinking about vapor permeance that way. It's a characteristic of every material that's in our wall. So being aware of the relative permeance or ability to dry of every single material that we put in our wall assembly is something that we ought to be doing anyway. And that should like precede any conversation about barriers or retarders or membranes that we specifically select to fulfill this kind of purpose. And I think that gets lost a lot too. People don't realize, they say like, where does the vapor barrier go? Well, what are you building with? And this comes up in other building materials too, like air barriers, right? Is a classic example. Like concrete's a pretty good air barrier. You know, if you seal the cracks or any kind of joints, concrete's a great air barrier. Sheets of plywood, of OSB famously are good air barriers if you tape the seams, tape the joints.
Some OSB.
Yes. Well, even that, I think, by the way, I think you're referring
Yeah.
to the RDH research on that, which is fair research, but like they found that sheets of OSB will leak air under like very intense pressures.
But there was also Mike's
Mike company had trouble
experience with it. Yeah.
Yeah. Or yeah, when I worked at EcoCore, one of our first projects was with commodity OSB, and we could not get, or we had done several projects at 0.4 ACH50, and we could not get this one below like 1 or 1.2, and we tried and did everything we could, and eventually did the test with the plastic over it, and it bulged out, and we Persocoed the entire interior of the house, and we got it down to like 0.2. So it's in talking with the manufacturers, it's probably specifically OSB made with aspen, which is in the north of the aspen. Somehow doesn't compress as well as the southern pine they use in the southern part of the country. But it was pretty interesting, and I saw it with my own eyes. So just I always push back a little. Yeah.
I don't believe that it's fake. I believe it's real, but I think we have to not confuse the test metrics for what the test metrics are meant to tell us. So what we care about is in-service performance. And I bet you if you compared the two different types of OSB, the one that the aspen and the southern pine, and you did tracer gas analysis for two identical neighboring houses operated the same way, I doubt you'd find any appreciable difference in natural, quote unquote, natural air changes. But you find big test differences or in blower door tests. Now,
Sure.
We're all in the industry and we need a metric that helps us here. So if using a material obscures the results, that's not good for us for other reasons. But it's also not true that like you're necessarily doing a terrible job. You've just made it so that this other tool, this blower door test, is less reliable, less indicative. Like it doesn't tell you all the valuable things you want it to tell you, like where you have other holes that need to get One of the things with the blower door test is it doesn't really tell you where the holes are. It tells you that you have holes. I mean, you can walk around and you can feel, or if you've got doing a smoke test or something like that, but it's like a flood test for that reason. If you're flood testing a plaza deck or something like that, it's good to do the flood test, but it doesn't tell you where the breach is. It just
Right.
tells you that you have one. So you better be able to find it.
Right. Or here's a question I get sometimes, and I don't have a good concise answer. How can a material block air yet allow what water vapor through? How can water vapor get through something that air can't? It doesn't make intuitive sense. So what is the chemistry that or physics or whatever that allows the
Molecular size.
There you go. I mean, think of
Yeah.
the size of the molecules. Yeah. And the way that the materials are sort of woven together. This is really hard, and I am not an expert in the chemistry here at all. But I guess the difference would be, I give an example. I'm a little bit of a beer in, so forgive me if I'm not real sharp with my example here. But if you think of like, I talked about having a wet towel in a plastic bag. If I put a wet towel in a plastic bag, and leave it, it's going to stay wet. And if I knot it up, it's going to stay wet for a really long time. If I poke a bunch of holes in the plastic bag, like 1,000 holes with a safety pin, even though I've poked 1,000 holes in that bag, what do you suppose you could actually calculate this like pi r square. You could like do the relative to the surface area of the bag and the number of holes. Even 1,000 holes or 10,000 holes probably actually still covers most of the bag, right? Like we're still probably at like 99% coverage with my plastic bag there. So even if I poke a bunch of holes in that plastic bag, if I leave the wet towel in it, it's going to stay wet for a long time anyway. Not quite as wet, but the drying certainly won't be, I'd be disappointed if that's how I was trying to dry my towel, right? And that has to do, molecular diffusion has to do with surface area, the properties of the materials that are in contact with each other, and the percentage of the surface that's covered, if that makes sense. Now, if I were to undo the knot I've got in my imaginary bag here, plastic bag, and I were to put a hair dryer, and I've poked the holes in, and now I'm pushing hot air into the bag and letting the air come out of the holes that I've poked in. Now I get to remove, now my towel dries quite a bit faster, right? And it's drying much better from air exchange and moisture removal from air exchange. And we have
pretty good. Christine, that brings up a question for me. I often see people when they're doing like sub-slab vapor barriers meticulously detailing every little penetration where a pipe goes through and taping it and sealing it as if it was an air barrier. Is that really necessary?
Yes and no. That's a great question. So if all we're talking about is controlling vapor for the purpose of not screwing up our flooring, say, or like our finished flooring that we install on top of whatever it is that we're doing. So we've got, below grade, we've got polyethylene, we've got concrete, and then we're going to put some sort of flooring down or something. Having the poly there, even if it's imperfect and the seams aren't taped and you've walked on it with golf shoes or whatever, will do a great job of preventing 99.5% or whatever of the moisture in the soil in the vapor form from diffusing through that slab. But and this is again where terminology kind of leads us astray. We call that thing a vapor barrier, but we want it to do more than just control vapor. We often also want that membrane to be an air barrier, and we want it to control soil gases. Yes. And other stuff. So if all we cared about was the vapor, yeah, it'd be fine. We'd be fine. So if you have, let's say you've got it in another application, you're putting, let's say you've got a concrete roof deck and you're going to do roofing on top of it, and you want to keep that moisture in the concrete so it doesn't screw up your roofing system, like a commercial roof. So you put a vapor barrier, fluid applied vapor barrier down on your deck to keep you want the moisture in the concrete to stay in the concrete so it doesn't blister your roof membrane or make your insulation wet, blah, blah, blah. Let's now say that in that example, we've got pinholes, got a bunch of pinholes. Is that going to be a problem? Probably not. I mean, it'd have to be pretty pervasive pinholes because all we need that to do is keep the water in the concrete. Whereas sub slab, we often want that to control soil gases, and we want it to be an air barrier as well. You don't have to make the poly the air barrier. What you could do is you could detail the concrete to be your air barrier and seal your penetrations there, but you have to make that decision. Where am I gonna make my air barrier? And often it actually is easier to detail the poly to be continuous than the concrete, because concrete cracks unpredictably, and even small cracks. If we're doing something like soil, if we're dealing with soil gases, we can have a real problem there. Yeah, it's sort of, the terminology sometimes suggests to us it doesn't capture the full function of what it is we're trying to do. That poly is also a capillary break, but we don't call it a capillary break. We call it a vapor barrier. Does that mean we don't need it to be a capillary break too? Maybe. Sometimes we have another capillary break. We've got stones there, gravel underneath it, and we've got two capillary breaks. But sometimes we don't. Sometimes we need it to do both. But yeah, again, like, what do we mean by the words that we use? What do we use?
I think that the reason I asked that one is I think people think that vapor performs like air does, where you poke a hole in the balloon and all the vapor is all going to rush towards that one hole. And I think that for me, that was a critical distinction that I had to learn to understand it. It's like, your analogy about walking on that vapor barrier with golf cleats, or you're poking 10,000 holes in that bag, it's still 99% effective across the whole of it. Whereas if you poke 10,000 holes in your air barrier, you're going to have big problems.
Yes. Yeah. And that's another complicating part of our conversations about vapor, is because it's so closely tied to air control as well. And we'll talk about this when we're talking about walls. That's what people are often most concerned, or that's where they start. So the discussion about vapor usually starts in walls. And when we're dealing with vapor control in walls, we often want to control both air and molecular diffusion, the kind of little bitty molecules that move through a material even without air. So I tell people, when they're picturing that kind of water vapor movement, if you have something wet and you put it in contact with something dry, the dry thing becomes more wet and the wet thing becomes a little bit more dry. So my wet towel, if I throw that on my wood floor, my wood will get a little wet and my towel will get a little bit dry. And that water movement from the wet towel to whatever I've put in contact with it occurs via molecular diffusion. Now there's other stuff going on there too. Like, I'm just trying to come up with an intuitive example, and that kind of usually gets people thinking. So airflow, moisture movement, liquid water is obviously the biggest thing that we deal with in building design. And then the next biggest thing we deal with is water in the air moves with the air. Makes sense. And then the next biggest thing is this molecular diffusion, where water vapor, which is very, very small amount of water, will move through materials. And it's, an order of magnitude less important than the air movement, and certainly than the liquid water movement, but it still ends up mattering in a lot of cases, especially in cold climates. So that's I think most people who are familiar with building science know that order of magnitude thing, but I think we have this defect when we start learning about building science, like a genetic defect that makes us pick like the hardest part of it and focus on that, and then we feel dumb. Like there's all these things we don't understand. We get obsessed with water vapor.
I think that's the thing about, go ahead, Mike.
Or no, just I think it makes sense for those of us who are curious about how things work. Like it's kind of not, it's pretty simple to keep, well, it should be pretty simple to keep storm water out, bulk water out. Not that it is done as well as it could be, but it should be. That's easy. Air leakage is pretty simple. And so when you get to vapor, it's when it gets interesting, because you start to have to understand, like, what is this thing that you can't even see? What is it doing? And how is it affected by airflow and by temperature? Like, I had a project years ago that I ended up calling Bill Rose when he was still working, and asking him, I was trying to understand vapor drive and what vapor drive meant. So like if I had a cellulose wall that wasn't protected yet in cold weather in Maine, like during construction, would it only dry to the exterior, or would it dry somewhat to the interior? Just intuitively, I figured mostly it would dry to the exterior, but some of it would go to the interior. And he said, nope, it's all vapor drive. 100% vapor drive is the only thing that matters in terms of drying potential. And that just sort of was a big shift for me, just understanding that it's all about vapor drive. Do you agree that vapor drive is important? And can you explain what vapor drive is, or why it matters, or why it doesn't matter?
Sure. Yeah, I mean, it does. I prefer to sort of divide this discussion in two different parts to make it to sort of anchor the discussion and make it as easy as possible to apply in what we do. That's another issue with, I think, the way that this subject is approached almost too academically, where we get out the psychrometric chart and we attempt to teach people physics. And it's I don't know how many people that really helps, honestly. I find it helps some people. It really does. Some people's minds just work that way. But I find that to be a really difficult way to learn about it. So I prefer to think about, when we're talking about walls, I think about the two most common cases where vapor ends up being a concern. And there's really only two. I mean, there's variations on these themes, but there's two kind of categories. And I think that really helps people. So the first category is condensation control. And I'm holding my beer up here to show you how impressive it is that I'm still forming full sentences with 3/4 of a beer left. No, because this used to be a cold beer, and there was condensation on the glass. And understanding condensation in terms of cold surfaces is one of the most helpful ways to approach this architecturally from a building perspective. And so think about cold surfaces. For condensation to occur, we must have a cold surface. 100% of the time, there has to be a cold surface involved. And really, I mean, we're dealing with buildings. We care a lot about surfaces for all kinds of reasons. That's a lot more intuitive. So I really don't like when people start talking about dew points and moving the dew point from one place to another place. It is so abstract and it's really difficult. Also, the dew point being the point at which condensation will occur. If you do this calculation or dynamic analysis and you find the point at which the dew point in your wall, condensation will not happen there. It will only happen at a surface. This is a surface problem. And there's a whole bunch of interesting physics as to why that's the case, but we don't have to get into that. But
even then, it doesn't always happen on surfaces.
Exactly. Anyway, but this is a surface issue. And that's sort of funny language. But anyway, this is a surface issue. Do you have a cold surface in your assembly? So if you've got a cold beer, warm day, you get moisture, usually moisture-laden air that comes into contact with a cold surface and you get condensation. So this is pretty intuitive for people. We do on grass. It's condensation sweat on your can of soda, on your can of beer, whatever. And the same thing happens in our buildings on surfaces within our wall assemblies. If we have a cold surface, we will get moisture, warm interior moisture laden air, usually interior moisture laden air that reaches this cold surface and our cold surface in our assemblies, and we get condensation. There are only 4 ways that we can address condensation architecturally. Only 4 things we can do. Actually, just in general, there's only 4 things that we can do to address this. So the first thing is get rid of the cold surface. So make the cold surface warm. And we can do that by heating it. Like you could actually heat it up if you wanted, in theory, or you could insulate it, right? Insulate it on the outside. So heat the cold surface. One thing to do with condensation. The second thing to do is somehow prevent the moisture from reaching the cold surface. And that's when we start talking about membranes and detailing things to be continuous or whatever, but prevent the moisture from getting to the cold surface. The third thing that you could do is you can remove moisture from the environment. Now, this is a kind of tricky one. You could dehumidify, basically. This is sometimes, like, practically speaking, if this were a really cold beer and we were in Texas in the, let's say we're in Houston in August, you'd have to really dehumidify to not get condensation on your can or your bottle. But you theoretically could remove so much moisture from the environment that you could prevent it anyway, or at least significantly reduce it. And then the fourth thing that we can do to address this issue is to permit the condensation, allow it to occur, but make it so that it's not problematic for one reason or another. So a great example of that is me drinking my beer. I'll get condensation on this. And so,
Yes.
okay, like, all right. So like, I can't drink this. There's condensation on it. Yeah, it's and in building design, what we typically do is we either use something that's not moisture sensitive, which is unusual, right? We build with a lot of moisture sensitive things, or we permit drying. And as long as the wetting isn't excessive or very prolonged, if we provide enough drying, we can deal with the issue. Now, so those 4 things: warm the condensing surface, prevent moisture from getting to the cold surface, dehumidify, and provide drying. Essentially, those are our 4 approaches, and we almost always pursue these in combination. So if we look at, I will share my screen now. Let's just share. You're just gonna, no, I'm not gonna show you everything because I don't know what's on my computer. Well, my dog is here, so you can see Katie. But here, let's look at condensation. So here are the 4 things we can do here. But if we look at a completely standard cavity insulated wall, can you guys see this now?
Yes.
Okay. So if we look at, this is the completely standard cavity insulated wall, right? We've got a cladding. It's just a generic cladding. We've got a water and air control membrane, an airspace behind our cladding, a water and air control membrane, exterior sheathing, usually OSB. And then we've got our cavity insulation and our interior drywall. And let's say that it is winter and it is warm inside and it is cold outside. And this is something we should just, like, when people are learning this, they should just memorize this. Like, look at the standard cavity insulated wall, not memorize, but like walk themselves through why it works. So where is the risk of condensation in this wall? It's on the interior face of the exterior sheathing, where I've just shown there. This is standard. Like, this wall is so common. We should teach starting with the most common way we build. So this is where our risk is, the interior face of the exterior sheathing. This is almost always what ends up concerning us, is how cold is that surface? And when we look at this particular wall, we build this in a lot of cold climates, right? So why aren't all of our walls rotting? This wall tends to work reasonably well. Why does it work? Why does it work? If we go back to this, What are we doing here?
I didn't get that.
Oh, Siri doesn't get that. Why? I just started wearing my Apple Watch again. But anyway,
Tell Siri she's drying to the interior. It's fine. Calm down.
Siri, calm down, calm down. So anyway, so why does this wall work? And this is why. So we have a vapor open water and air control membrane that permits drying to the exterior, and it dries into that airspace as well. So the better we ventilate our cladding, the more exterior drying we get as well. That's a nice feature of rain screen assemblies or drained assemblies. And then we have an interior air and vapor control membrane that reduces wetting. Now, sometimes we actually pick a separate membrane. I've got that drawn in here. I don't know if you can really see. Let's see. I've drawn a dashed line here, but oftentimes we rely on just the interior drywall to reduce how much warm interior moisture laden air makes its way to that cold surface, right? Incidentally, where's the riskiest spot in this wall? For people listening, it's right here, where we don't have as much exterior drying through our framing at our floor lines. So how do we address that? We bring our drywall all the way up and we air seal, or we use spray foam here. It depends on what we're doing in whatever climate, or we use rigid insulation and air seal, or whatever. We're attentive to this. But we're relying, if we go back to our condensation example, in our most standard wall, what we're doing is a combination of 2 and 4. So we're not letting moisture or as much moisture reach the cold surface, and we're permitting the condensation, but we're permitting exterior drying. So we're doing both of those things. Now, we're kind of sort of sometimes doing this in that we do something often to control relative humidity inside. If say we did, we can stress this wall, this standard wall, if say we have, instead of a single family home with 4 people, we have 8 people living in that house, and they're cooking, cleaning, working out, whatever, that can stress this wall to failure. But this is a very fine balance of wetting and drying. And people sometimes think like that we're engaged in condensation prevention when we have this discussion about condensation control and water vapor. And that is not what is going on here. In cold climates, and in fact in warm climates too, like I routinely get condensation on my wall. Wow, it's really dark where I am now. I'm gonna have to turn on my light in a sec here. But well, actually we're almost at the end, but we'll get condensation all the time on all kinds of walls. The question is, do we get it for long enough to create a problem? And that the answer is often no, we don't. But I think people, when they start learning this stuff, they can get sometimes very angry and also sometimes very scared. Very angry because they're like, wait, it shouldn't be this way. I should have 0 condensation ever. And very scared in that. So those are the 2 responses I see when I teach this. The anger, like there should be no trade-off. Like we shouldn't be doing this. We should have the tolerance for condensation should be 0. We should never have it. And then the other response is to be sort of scared at how close to failure we really are a lot of times. And that should make us kind of maybe not scared. I don't like to do things in fear, but it's certainly sobering that this standard wall is a very fine balance of wetting, drying, and safe storage, and we can stress it to failure if we're not careful. Anyway, so this is one sort of like bucket. I said that there were 2 ways of approaching water vapor, and this is the first scenario: is when we're dealing with cold climates, wintertime, or actually not even cold climates, any climate, but we're dealing with a wintertime problem, and our moisture source is on the interior. And we do something to address condensation at this surface. And this is the most standard way of dealing with it. Other ways of dealing with it, of course, are providing exterior insulation, right? warming, if we warm this surface, that ends up being a far more reliable way of dealing with this issue than policing the integrity of this membrane, typically, not always, but typically. And if we use an insulation, say mineral wool, that's also vapor open, or EPS, we still get exterior drying through that membrane, or through that, whatever it is we're using, which is awesome. Now it works if we use something completely impermeable, like foil-based polyisocyanurates, but you want to be really careful that you use enough of it, right? If we don't make the surface warm enough to address this issue, now we've reduced our drying capacity, but we haven't fully fixed our
So Christine, can I interrupt you for a second? So how safe are the IRC guidelines for ratios? Are they pretty, cut and dry, that if we adhere to those, we're in safe ranges?
They tend to be pretty safe for standard use buildings. They are not safe enough for buildings that we keep at elevated relative humidities, say in response to COVID and pathogen control. So if we want to start humidifying our buildings and keeping relative humidity at 50–60%, we're going to need a lot more exterior insulation to avoid rotting our buildings out. That's a great question. Second thing, I did not know this, but I posted on this recently on Instagram, and someone responded with some research that has been done in Alaska recently. And so in climate zones 7 and 8, they did some research that seemed to suggest actually that the ratios in the IRC are a little too minimal. That now the research it's very difficult to conduct this research because people like to keep their interior environments at different rates. So
my wife likes to pack my house full of potted plants and water them gallons of water every day, and
people live differently.
There you go.
Exactly. And it really skews the research. So it helps to be informed about this stuff so that you can make trade-offs accordingly. If you know that things are going to be more humid inside, that you add more exterior insulation. But I was actually, after like really looking at the commenter was being really nice, but it was like semi-trollish. If he's here, I don't want to say that. It wasn't like that. It was in good faith, but I think he not deliberately, I think he kind of misunderstood some of what I was saying. But anyway, regardless, it made me really go and look at the research. And I was like, actually, I think I want to revise my own recommendations to people based on the Alaska case. And then I think there's a good case to up for the IRC to increase this, all in response to people wanting to keep their interior environments more humid. But there's
now let me throw
difficult, right? Like this is expensive.
Yeah. Let me throw a twist on that. Can we start to bend those ratios if we're using more vapor open exterior insulations?
I don't think that I would parse. I think different professionals will give you different answers on that. Personally, I wouldn't stake the performance. I wouldn't bet my professional integrity on that. I would want to exceed. I'd really want to be conservative with that. And I'd want to use a vapor open exterior insulation and exceed those ratios. But yes, you can. And actually the code tries to do this already, but the code, I don't think does it very well right now. It's written in a really confusing way, but the code allows you to trade these things off, right? So people will know if they're building in cold climates, they know that the interior vapor control requirements, like whether or not you have to have a membrane here, depends on a bunch of different factors, in that the code will let you remove this if you're using enough exterior insulation and if your cladding is back vented and drained, if there's an airspace. And the reason is because of this, right? So it allows you to trade number 1 for number 4. So we can tolerate a slightly colder surface if we provide more drying. So it lets us parse these things off, but unless you really understand this, you might be introducing more risk into your designs than you really realize. And I'm gonna have to go in just a moment. People can maybe stay anyway, but I wanted to get to the second category where water vapor matters that Michael asked me about like 20 minutes ago. So this is the first case, like we're dealing with a wintertime issue. This is, and just memorize this, like, why does a standard residential, why does this wall work? Oops, oh, that wall too. Where am I here? Why does this wall work? Like, why does this wall work? Our completely standard wall work. And then what could you do to increase or decrease risk? Like, so if you add insulation, does that increase your risk or decrease your risk? How? Does it matter what kind of insulation? Ask those questions. So compare this slide to this slide and push and pull, and that'll help get you more conversant in what's at play and the physics at play here. And then the second category of issues for us has to do with this inward vapor drive. It's almost always inward vapor drive. It's not always, but this is like the most common. So we're talking about the two most common scenarios. The first one is this wintertime issue that will make us want to consider interior vapor control. That's our first issue. And then our second issue is what happens when we've got a wet, sunny climate and we are using a reservoir cladding or cladding, so any kind of cladding that holds a lot of water. So that cladding gets saturated in a rain, the sun comes out and drives that water both inside and out. But this water we don't really care about. The water that goes into the wall can overwhelm the wall's capacity to dry. And we can do things that make this even worse for us. So for example, we could use a polyethylene vapor barrier. And that could be a big issue because now we'll get condensation on this surface anyway. And we might overwhelm the wall's capacity to dry anyway. But we will definitely have a problem if we've got polyethylene and we air condition. And now we've got condensation that can't dry to the interior, and we can get this, get mold. Same issue with vinyl wallpaper, that kind of thing. Interestingly, these rules still apply to this scenario. So to this scenario, right? So there are things that we can do to reduce this effect that that maybe aren't that intuitive. So we can reduce it. One of the things that we don't realize, people don't realize what we're doing here, is this. So having a ventilated cladding, we tend to think of that as being only about draining water out, having an airspace behind our cladding. That is not the only thing that's going on there. And actually, we really only need a very, very, very small amount of space behind our cladding, between our cladding and our WRB here, water control membrane, to provide drainage, even in very wet climates, like 1/8 of an inch, less. I mean, whatever, we'll be fine as long as it's continuous and can drain out for water management, for liquid water management. Where it helps to have a nice big space there is in controlling inward vapor drive from having reservoir claddings here. Because what we do is we can flush that moisture out before it even gets into the wall. And it allows us to do stupid things like put poly on the interior of our wall. That's a little bit of a joke. You could still use poly if you're in Canada, but that's incidentally, that is why the Canadians sort of get away with having poly on the interior and using that as to solve their wintertime problem, is because they're very, very good in Canada about getting a lot of ventilation behind their claddings. So we can have real problems if we don't have a very big airspace and don't have ventilation, and then we put some sort of membrane there, like stucco, for example. We don't have a big, the stucco's right there, right up against our membrane. We get that water just gets driven straight into our wall via vapor diffusion, not liquid water. And it can overwhelm the wall's capacity to dry. So anyway, I like to teach it in these two, like these twin concepts of solar vapor drive, exterior solar vapor drive, which by the way is not a warm climate, cold climate thing. It's a sunny, wet climate thing. So this is a problem in Toronto, in Boston, in Chicago, and it's a problem in Houston too, and Miami. Now it tends to be worse, obviously, in Houston and Miami, but there are humid summers and cold climates, and sunny. This is a sun issue, sun and wet issue, not just a temperature issue. And I think people have a really hard time with that because of the way they probably first learned about water vapor, where they think sort of more simplistically. But anyway, they can be forgiven for that. It's hard. This stuff is hard. It's natural to want to find some rules of thumb and ways of simplifying this kind of stuff. That's the way that I found work. I hope it kind of helps with people who have listened. Even people who know this very well. I love hearing other people talk about how they conceive of vapor control, because it's hard, and anytime somebody talks about how they understand it, it helps me understand it better too. But with that, I'm gonna have to sign off and miss some of the conversation, the rest of the conversation, because I want to kiss my son before he goes.
Or,
Or
just-
That's perfectly okay. We're actually moving BS and Beer hopefully this year to an hour long. So this is perfect timing and good for us to, kind of go over with the crowd who's still here, who joined us, that we're going to shorten things up a little bit this year because everybody's time is precious. So there were a couple of people who wanted to see the kid. I don't know if you're sharing.
Yeah, he's with my husband right now. I would know. He's really cute. I mean, just picture the cutest possible thing, like the platonic ideal of cute. That is my son. It's amazing. They make him cute on purpose.
You're not biased at all, are you?
No, not at all.
No.
Although people do stop me in the grocery store a lot, so just saying.
Yeah. Or well, Christine,
There's your
thank you.
retirement fund.
That's right. That's right. Anyway, I really am going to sign off, but be polite.
Yeah. Thanks a lot, Christine.
Thanks, Christina.
Yeah, and if viewers want to learn and understand more, Christine has various courses ready to go. Emily is teaching a course that is, I think it's already launched or semi-launched, and that's in the works. So there's multiple, probably written 10 articles and done videos on vapor management. So there's a lot of resources out there if you want to learn more. I think we could talk about vapor for hours and still not understand it, and still have people confuse air movement and vapor movement. But
Maybe the first show every year needs to be on vapor. We're just going to keep repeating it till everybody gets it.
get the basics down. What is vapor?